These street lights don't need a switch, they think on their own. This Java project simulates an LDR sensor detecting daylight. As sunlight fades, the sensor triggers every lamp to glow automatically. When it's bright again, they switch off, saving power instantly. Smart code. Smarter streets. Now let's create our Java class, Smart Streetlight Demo. This class will handle the complete LDR simulation. First, let's import the required Java libraries. AWT gives us access to all the drawing and color tools for our graphics. Swing is used to build the window and user interface. Event helps us listen for slider movements, just like our LDR sensor. Now, we'll make our class extend JPanel and also implement change listener so that our program can react whenever the slider value changes. Next, we'll generate the state changed event. This method runs automatically whenever the slider is moved. Now let's declare our main variables. First, we create a JSlider called LightSlider. This will act as our simulated LDR sensor. Next, we set an integer variable ambient light to 100, representing full daylight at the start of the simulation. Finally, we define a constant threshold value of 40. Now let's add the class constructor method for Smart Streetlight Demo. Inside the constructor, we start by setting the layout to border layout. This layout helps us organize different parts of our interface. Then we set the background color to black, which gives our panel a dark base, just like a real night sky before the lights turn on. Next, we create our slider using new JSlider constructor. This means the slider will range from 0 to 100, starting at the current light level. Then we call setPaintTicks true and setPaintLabels true so the slider shows tick marks and numbers for easier control. We set major tick spacing to 20 and minor tick spacing to 5 to give it a smooth, clear scale. Finally, we add change listener. This connects the slider to our class so that every time the slider moves, the state changed event will run and update the simulation in real time. Now we'll add a label to explain what the slider represents. We create it using new label with the text ambient light, LDR, 0 equals night, and 100 equals day. The swing constants .center keeps the text perfectly centered. Then we set the text color to white so it stands out on the dark background. We apply a bold sans serif font at size 14 for a clean, modern look. Finally, we add a small empty border using Border Factory to give the label a little breathing space from the edges. Next, We'll create a new panel called Bottom using a border layout. This panel will hold both the label and the slider neatly together. We set its background color to dark gray so it contrasts slightly with the black main panel. Then, we add the label to the top position using border layout, north, and place the slider just below it in the center. Finally, we add this entire bottom panel to the main layout at border layout, south, positioning it perfectly along the bottom of the window, just like a control panel for our street light simulation. Now let's create a helper method called drawLampPost. This method is responsible for drawing each individual street light on our screen, including the pole, the lamp head, and the glowing light when it turns on. The parameters here are simple. G is the graphics object we use to draw, X is the horizontal position of lamp, ρ is the position of the road so we know where the base of the pole goes, and light on is a true or false value that decides whether the lamp should glow or not. Inside the method, we first convert our graphics object G into a graphics 2D. This gives us smoother, more flexible drawing functions for shapes and colors. Next, we define two integers, pole height set to 120, and pole width set to 6. These determine the size of each street light pole on a screen. Next, we set the color for the pole using new color 70, 70, 70, a medium gray shade, and draw the pole using fill rect. We position it by subtracting half the pole width from the x-coordinate to center it, and we extend it upward by the height we defined earlier. This gives us the main vertical structure of the lamp post. Then we move on to the lamp arm. We set an arm length of 25 and use another fill rect to draw a short horizontal bar at the top of the pole. This arm holds the actual lamp head. It adds a nice realistic touch to our design, showing how street lights usually extend over the road. After that, we calculate the lamp head position. We create two new integers, lampx and lampy. The lampx is simply the pole's top position plus the arm length, and lampy is slightly higher than the top of the arm. With these coordinates, we draw the lamp head using fill round rect. The color is a slightly lighter gray, 90, 90, 90, and the rounded corners make it look smoother and more realistic. Now comes the interesting part, making the light glow. We check if light on is true using an if statement. If it is, that means the sensor has detected low light, so our street light should be turned on. Inside the if block, we change the color to a soft yellowish glow. We then draw an oval shape around the lamp using fill oval, slightly offset from the lamp head to simulate a spreading light beam. This gives the visual impression of light shining downward onto the street. If light on is false, we simply skip this part, and the lamp stays dark. Now let's move on to one of the most important parts of our project, the paint component method. This method is automatically called whenever the panel needs to be redrawn, which means every time the slider moves or the light value changes, this method refreshes what you see on screen. Calling super paint component is a best practice in Swing. It clears the old frame before painting the new one. preventing unwanted overlaps or flickering effects. Next, we get the current width and height of the panel using getWidth and getHeight. Now comes a very cool part, the sky color transition. We create a float variable t by dividing ambient light by 100. This gives us a value between 0 and 1, representing how bright the environment is. Then we define two base colors, one called night, a deep bluish tone using new color 5, 10, 25, and another called day, a bright sky blue using new color 135, 206, 235. These two act as the endpoints for our gradient, night and day. To make a smooth transition between them, we calculate the red, green, and blue components separately. For each channel, we take the night color value and gradually blend it with the day color using the factor T. This line-by-line color interpolation gives a realistic fade effect between day and night. After we calculate these three RGB values, we create a new color and fill the entire panel using fillRect 0, 0, W, H. Now, as you move the slider, the sky will smoothly change from dark blue to bright sky blue, giving a real sense of the day and night cycle. Next, we draw the road. We set a variable roadie to about 65% of the total panel height using h into 0.65. This defines the top edge of the road. We set the color to a dark gray, new color 35, 35, 35, and fill the lower part of the screen with a rectangle. This becomes the street area where our lamps will stand. Now it's time to decide whether the lights should be on or off. We create a Boolean variable called lightOn, which becomes true when the ambient light is less than our defined threshold. So, when the simulated light drops below 40, all street lamps automatically turn on. Then, we set up the number of poles, in this case, 6, and use a simple for loop to draw them evenly spaced across the screen. Inside the loop, we calculate the x-coordinate for each lamp post, multiplying the index by the width of the screen and dividing by the total number of poles plus 1. That ensures even spacing, no matter the window size. For each lamp post, we call our drawLampPost method, passing in the graphics object, the x position, the road's y position, and the lightOn boolean. This lets each post know whether it should glow or stay dark, all controlled by our slider, the LDR simulation. Finally, we add a simple status display at the top left corner of the screen. We set a bold sans serif font at size 16 and color it white for clarity. Then we build a status string that shows the current LDR value, the threshold, and whether the lights are currently on or off. Using drawString, we print that information directly onto the panel, giving the viewer a live update of the system's state. And that's the entire paint component method. It ties everything together: dynamic sky color, road, lamp posts, and real-time LDR updates. Inside the method, we first read the current slider value using LightSlider.getValue and store it in our ambient light variable. This instantly updates the light level of our simulation. Then we call repaint, which refreshes the panel and redraws everything: the sky, road, and lamps. Finally, let's complete our project with the main method. This is where our program actually starts running. We call swingutilities.invoke later, which ensures that all our user interface code runs safely on the swing event thread. This is the recommended way to start any Java GUI application. Inside the Lambda expression, we create a new JFrame and give it a title: Smart Streetlight Automation, LDR Simulation. This frame is our main window that will display everything we've built so far. Next, we set the default close operation to exit on close so the program closes properly when the window is closed. Then we set the size to 800 by 450 pixels. We center the window on the screen using setLocation relative to null and make sure it can't be resized by calling setResizable false. After that, we add a new instance of our Smart Streetlight demo class to the frame. This is the panel that handles all the drawing, logic, and animation we've coded so far. Finally, we call setVisibleTrue to display the frame. And that's it, our full simulation is now complete. When you run the program, you'll see the slider, the changing sky, and the smart street lights that automatically turn on and off based on ambient light levels, just like a real-world LDR-controlled system. And that's how our smart streetlight automation project works: simple, smart, and energy efficient. If you enjoyed this demo, don't forget to hit the like button, subscribe for more Java science projects,